Welcome to Radio Frequency Integrated Circuits Design class, and this is your lecture 9, Unit 2. And in today's class, we will see the graphical analysis of image reject receivers. So, in the previous class, we have discussed. Yeah, in yesterday's class, we discussed about how to implement a degree phase shift, and we saw how HSI and LSI, how this HSI operation and LSI operation will shift the signal, and with that we have concluded. We have taken 2 points. So, if you perform HSI, the Q component will be the Hilbert transform of the I component, and for LSI, the Q component will be negative of the Hilbert transform of the I component. Right. So, this is what we have concluded from the discussion then. And after that, what we have done is we have taken a signal, RF signal. The spectrum what you are seeing on the screen now is the input to this part. We are trying to develop the architecture of an image reject receiver. So if you look at this, look at the input signal spectra, you can see the signal as well as the image, and the local oscillator is placed in such a way that for input signal it will be LSI, and for image it will be HSI. So that is what you are seeing here on the screen. Now this input signal is actually given to this input signal is given to two mixers. On the upper arm, the I arm will be multiplied by cos omega LOT, the local oscillator frequency, and the lower arm or the Q arm will be mixed with the sin omega LOT. And after that, definitely on the upper arm and lower arm, we will get signal along with image. So the upper arm component is marked as I signal and I image, and the lower arm component is marked as Q signal and Q image. So with this input signal spectra along with the image, we have drawn the I component and the Q component of signal and image here, right? Yeah. So we have drawn only signal. Yes. So this is the signal component. So this is a signal component. What I'll do is let me just take this. So this is the signal component of the signal. So this is a signal component where in phase component is marked as red, and the out of phase component, sorry, the quadrature component is marked in green. So similarly, if your input signal spectra is passed through two mixers, you will have images also. So to plot image, let me take the spectrum, and this will be for the image. So image is located at, it will be located at omega IF. So the in phase component of the image I'll mark using this color, the same color, the red color. This is the in phase component. Since it is multiplied by cos omega LOT, now the okay, now I need to mark the amplitude as well here. So the amplitude will be, this will be B by 2 and this will be B by 2. Now the quadrature component. So to draw the quadrature component, I'll just make a note here. So here what I am drawing here is signal. Signal is having I signal and Q signal, right? Now since for signal it was LSI, low side injection, the Q component, which is in green, will be the negative Hilbert transform of the I component, right? So the I component is in red, The negative of the Hilbert transform is what you can see as the green component on this on the signal spectra. Now, so the same thing on image. So for image also you have I component and Q component. Now for image it was HSI, right? How am I telling that it is HSI? Referring back to the previous slide, for image it is HSI, and for signal it is LSI. So since for image it is HSI, I can write that the Q signal component will be Hilbert transform of I signal component, right? So if that is if we know that if it is the Hilbert transform of the I signal, what I can draw here is I'll again use the same color, green color. So this will be the quadrature component, and on the other side we'll have this as the quadrature component, right? So you can see that yes, there is actually a 90 degree phase shift here, and here also anti-clockwise direction there is a 90 degree phase shift. Yes. So whatever you are seeing now is that is the signal and the image at these 2 points, this I and as well as this Q, right? So I hope this is clear. I have
Why for image it's LSI? I mean, why for signal LSI? It's
uh,
HSI.
no. So as per this spectra, for this signal it is LSI, right? The local oscillator frequency is on the left side. It is low side injection. Rakshak, hello.
Yes, sir. Yes, sir.
Okay, okay, all right, yeah, yeah. Anirudh, I saw your thing. I'll look into that. So the lecture 8 is redirecting. Probably when I copied the link, there was a mistake. I'll do that. Yes. So I hope it is clear. So the reference is this. The input signal spectra is this. So see, this is what I am considering now. We can actually consider the other way also, because that so if I am giving if I am doing HSI for input signal, then there will be differences in the spectra how it is coming out, right? Yeah. So currently I am taking for signal it is LSI, right? So now, so the aim is where we started is we need to cancel images and we need to retain signal. That is our point, right? So what we do now is now we have the components in this way. Now, in order to cancel image, or see, by keeping in mind that I need to cancel image, what I will do next is I will apply. Yeah. So what I'll do, I'll apply. So with reference to this diagram, I am actually going to apply another 90-degree phase shift only to the Q path, not to the I path, only to the Q path. Right. So again, to perform that, I'll take this entire thing over there. Right. So this is your signal and this is your image. Now I am going to perform a new operation. Now what is that? I am trying to give an 90-degree phase shift to the Q path. Now giving a 90-degree phase shift to Q path is as same as multiplying by minus j signum of omega, right? So what I'll do is to the Q component I'll multiply with minus j. If I can do that, yeah. So one thing I missed here, I need to mention the amplitude of this Q components. Uh, can you tell me what will be the amplitude of this Q components here? Can I get response in chat box? Amplitude of this green components, what you can see. Yes, minus jb by 2 and plus jb by 2. Very, very true. Yes. So it is minus jb by 2 and this is j into b by 2. Yes. Right. Now, since I'm going to perform one more operation on the same diagram, I'm just using a new color here. Right. So now, since I need to do 90-degree phase shift to the Q path is what you are seeing in green. So I have to multiply that component with the minus j. Right. So what I'm doing here is Q signal is multiplied using minus j on the right side, and on this side I'm actually multiplying using j. Right. It is minus j signum of omega. So similarly, I have to perform the same operation even here. This has to be multiplied by minus j, and this has to be multiplied by j. This is what I should do here. So Q signal I did. So along with Q signal, I signal also, sorry, Q image also need to be given this 90-degree phase shift. So when I write Q signal into minus j, that is on the right side. So here it is actually, yeah, I think that is very clear. What I'm going to perform is giving a minus j, I am multiplying with minus j to on the right side and j on the left side. Right. Now, if I perform this, what will be the result? So here the green components, it is j square will be minus into minus is plus. So what it will result is you will actually get one more component here along with a, right? So I will just overwrite on this and I'll write this as a by 2. I don't know whether you are able to see the color difference. So that will happen here, and similarly in this side also, when I multiply using j here, j square is minus is plus, so you will get actually plus a by 2, right? That is what happened to the signal. So signal, when we have given 90-degree phase shift to the Q path, the signal got added up, or the signal component got a real amplitude. It is a by 2 plus a by 2, and resulting thing is now a. Right. So let me just give a small representation here at omega if and at minus omega if. Now I have component with, this is my real axis, right? So this is real axis. So now this is with the amplitude of a. This is imaginary and this is real axis. Similarly, if you look at the image component, all right, Nikhil. I hope you remember what we have done in the last class. In order to perform 90-degree phase shift operation, what we did here, I didn't write that. Oh, I didn't. Oh, sorry, I didn't perform that yesterday. Okay, so I remember I have 1 second. Let me just check. Yes, here. Yeah. Can you see this, Nikhil? I remember I have written one equation also. Okay, I didn't do that. Let me write that here. So if I want to apply 90-degree phase shift to a signal, it is as same as multiplying with minus j signum of omega into x of omega. X of omega is the original signal. Yes, yes, Nikhil. Yes, thank you for asking. Probably others also. Yeah, it would have helped others also. Right. So similarly, when I perform this operation on the image, you can see now what you have is on is with green color. When I multiply that using minus j, minus is plus, j square is again minus. So what I will get is a component here with an amplitude minus b by 2. Similarly, on this side it is j into j minus, it is minus b by 2. It is minus b by 2. Right. Now, if you look at this after performing this operation, it is clear that the signal components got added up and you have the resultant signal as A at omega if. Now, the image components, what happened is image components now have opposite amplitude, or the in phase and quadrature components are equal but opposite in nature. That means if I do some suitable operation on this, we can cancel out images, right? So let me just draw before doing that. It is clear that if we can add up these two, definitely images will be cancelled and signal will be added up. That is what it is clear from that. So let me draw that picture here. So we have this input RF. Now input RF, what we did first is we have actually applied that to two paths. We generated in phase and quadrature phase components. For that I multiplied to one phase I multiplied sin omega LOT, and to the other phase I applied cos omega LOT. Right. Uh, all right. We were referring to upper arm and lower arm, right? Yeah. So this is cos omega LOT and this is sin omega LOT. So you can consider also in this form ALO cos omega LOT, and we haven't taken ALO, take just ALO as 1, the amplitude as 1. Now after performing this operation, yeah, so when you perform this operation, if you remember, you will actually end up in two frequencies. Since it is a mixing operation, you will get two set of frequencies. So we have to do a low pass filtering operation here so that the some components can be removed. So low pass filtering operation should be done. That we haven't shown. Yeah, we haven't explicitly shown in the diagram. We just have drawn only the difference component. Right. So you will get here, say if I mark this as omega c, we'll get omega c plus or minus omega LO components, but we are looking only for omega c minus omega LO component. Since for signal it is low side injection, our intermediate frequency of interest will be equal to omega c minus omega LO. Now, after low pass filtering, what we have done is we have applied a 90-degree phase shift to the Q path or the quadrature path. So here we have to apply a 90-degree phase shift. So that also we have done. Now the final result, the result from here and here, if we can add those two things together, if I add these two together, this will end up in an IF output where the signal components will be added up and images will be rejected. Right. I hope this architecture or this block diagram makes sense with what we have done in prior. So to get the final IF, we know that images will be cancelled out and signal. This will be your final IF output. This will be the IF output. Right. So this architecture is called as Hartley image reject receiver. Hartley architecture for image rejection. Right. So yeah, let me just mark the components. We'll do a mathematical analysis also after this graphical analysis. Say this is x of t, and here you will get the in phase signal and in phase image components. Here you will get the, sorry, here will be your I signal and I image. Here is the Q signal and Q image, but the images will be cancelled out when we add it together after the 90-degree phase shift operation. So this is the architecture of image reject receiver, and I hope this is clear for you guys. Now let me ask one question. So here we started with this for input signal. We have assumed LSI, right? So that resulted in this image reject receiver. Now say if I would have started with this, if for input signal, if I have taken HSI, what will be the result? Can I get response in chat box? Yeah, only image. Yes, yes. Anirudh, what I'm asking is, I'm not without changing the architecture. The architecture remains same, but if I would have taken HSI at the input, that was my question. Yes. Yeah. So that will ultimately result in something called as signal reject receiver. That is not actually we intend. Right. Yeah. Then suitably we should modify the architecture. If that is the case, we will result only in images. We will not get signal. Right. All right. So this is the architecture of this is what we call it as Hartley image reject receiver, and we have to perform a mathematical analysis also. So let me just write that and finish. So to after that, I can open for discussion if you have any doubts. Yeah. So I'll write the input signal x of t. While writing input signal, I'll just write that there will be an amplitude. I'll write it as a signal, and it is cos omega ct with a small phase shift. I call it as phi signal. Plus this is the image amplitude with cos omega image of t plus phase shift on the image part. Right. This is the original input signal what we have taken first. Right, the original input signal. Now let me write a few points here. If I consider this point as A, say this as B point and this as C. So can you write the signal at xa of t, xb of t, and xc of t? Can you try to write the signals at xa, xb, and xc of t, so that when we write if output, when we write the final if out, that will have only signal component. Images will be rejected. Can you guys try? All right, so how can I write xa of t? Xa of t is basically x of t multiplied by a lo cos omega lot, right? So maybe we will take ALO as 1 only here also, so that we no need to repeat that ALO again and again. So XA of t will be the original input signal x of t multiplied by cos omega LOT. So that means I will get XA of t as A signal by 2 cos of omega c minus omega LO into t plus this shift plus A image by 2 cos of omega image minus omega LO into T plus phi image. So while writing, I'm just since it is low side injection for signal, I'm writing it as omega C minus omega LO. Yeah, on the other side, I think we can write the other way. Now xb of t, xb of t is actually after performing, yeah, xb of t is actually after by multiplying with sine omega LO t. So you will get a component minus a signal by 2 sine of omega c minus omega LO into t plus phi signal. Yeah, you can actually perform the operation and see are you getting the same equations or not. Minus a image by 2 sine of omega image minus omega LO into t plus phi image, that is xb of t. Now apply 90 degree phase shift to xb of t so that I can write what is this xc of t, which is a signal by 2. This becomes cos omega c minus omega LO into t plus phi signal minus a image by 2. It will be cos omega image minus omega LO into t plus phi image, right? So now your IF output is IF output is actually the sum of xa of t and xc of t. That is IF output. So that will result in only the signal component. A signal by 2 and A signal by 2 will get added up, cos omega c minus omega LO into t plus phi signal. So this is how mathematically we can prove that this Hartley image reject receiver will reject images and will retain signal, right? What I would say is you guys can try this and check whether you are getting the same answers. So we will wind up this session here and we'll do a small activity.